Hello and welcome to the deep learning course. Today we're going to use the CFAR 10 dataset, and basically we'll be building our model from scratch using convolutional neural network until the prediction what is the main class of this dataset. So basically the dataset is different from the MNIST. For example, here is the data is it 3 channels, and also it have 10 clauses. If I check the targets, it will be a list. So if I need to uh, check how many image within each class, so the data is pretty much unbiased, and we here don't worry about the overfitting of this model. And as you can see here, this is 3 channel dataset, like red, green, and blue being inserted through this matrix, and we have only 50K image. Okay, so let's start to analyze somehow the set of images. Like for example, I will be using this um, to plot, for example, here 10 images while they are colored images. So I will be putting false onto this string brown binary string, which is to show them in a black and white. So as you can see here, we have 10 classes like cars, trucks, cats and horses, sheep, etc. So all these classes, we need to build a model to classify which of which is this image about. So basically, we are going to start first with a transformer, which would be applying some transformation to these images. And the transformation I need is to remove these colors and to make it a single channel. Because I assume I build an assumption like the colors can be misleading feature, because for example the brown car can also be brown horse, so the model can overfit on the color, and in that case we will be misleading our model to the class instead of if he learned anything about these colors. So anyway, we can first try. You can also apply it as you like with 3 channels. It's just a simple number, change it from the convolution. But from my side, I'll be transforming it into a grayscale black and white single channel. Okay, so as you can see from our last, there exists this compose method which hold a pipeline of transformations, and what I need is just to transform this into a grayscale. Okay, so by default the number of output channels is 1, so it will be determining the grayscale of this image. So for example here, if I have this image, there exists some image. Okay, so image is any random number, any random images. For example, I pick this 8th image, and let's try to transform it. Okay, so here it needs a BIL image, but it have a NumPy array. So the data within this CFAR data are in NumPy. If you can check them, they are not in tensors. Okay, so we need to take care of this because we need to transform into tensor in order to our convolution model to accept. So in that case, we need first, and before grayscaling, we need to apply PIL image format. So there exists this transforms to PIL image. So and insert the list comma. Let's put this up here and transforming. Okay, so now this is the PIL image. If I need to plot it, so for example, I need to plot this transformed image. In that case, I need image transformed, will be this image. And as you can see here, this is a BIL image. So it is just an icon. If we need to plot it, we need first to transform it into a tensor. So, so for example, here it doesn't have any shape because it's a BIL. Okay, it doesn't have this shape method. So we need to convert it back to be a tensor. So here we have also a transform dot to tensor, and here we can see the dimension of the data. It is pretty much 1 by 32 by 32. Okay, and if we need to plot it, sorry, we need to plot this, it will be this grayscale image. Okay, also if we have like a bunch of data and we need to transform them, like for example here this CFAR of data, and let's pick our first 10 images, and we need to apply transformation upon them. So like let's call this image batch. Okay, and for image in image batch we transform these, and image transform image batch transform it, and we can also apply concatenation on this list because it will be a list of 10 images, and we need to combine them. Like for example, if I need to determine, this will be a list, okay, and each item will be having this shape of 132 132. So if I have 10 images, I need to make it 10 32 32. So I need to have a batch of 10 images. So that's how we use this concat. So concat will be concatenating all these batches onto the first dimension. So now it should be 10 by 32 by 32 as we accept. Okay, and also to show all these batch in a single time, we can use this plotting, and it will be plotting all the 10 images that we have plotted before, but without any colors. That's a grayscale. And now let's building our data set. So our data set pretty much have these three popular methods: the initialization, the init, the len, and finally the this will be returning an integer. Okay, and finally the get item, which will be holding our transformation, and will be returning a dictionary. So let's first check the init. It will have the data, so I call it self.data, and it should take a data parameter, which is the CFAR dataset. Okay, so here we will be returning the length of our data, which will be used through our data loader, and it will be used through loading patches across our dataset. And after this, the get item, it will have it will return dictionary of two parts: the image, and it will be a tensor. So it will be self.data of x. This will be the image, and as a label. Okay, so also we need to pass not only the data but also the targets. Okay, so also the targets is needed, and here I need the targets of the index x, because x is nothing but an index. Okay, so we have this list of data or data frame or tensors. We need a single tensor out of it, and the data loader will combine them into a batch. Okay, so we need first here to apply transformation. So we need to pass tr here, like transformation process. We need to pass it as a parameter also. So basically, this will be applying a transformation into the data, because here we have a numpy array, so we need to apply this self dot transformation on the data on this item, and we can save it into image, or you can make it input image, and this will be a tensor now, and also in a grayscale and a single channel. Also, this target, we need to pre-process it to make it a torch dot tensor, because it is a list of scalar number. So this will be our target. Okay. So that's pretty much what we need to do inside this dataset. And if we run it, we can also check with an any input, like we give it the CFR, and the target is okay. This is CFR data of course, and this is CFR dot target, and the transformation is the object tr, and we check the first item, so it will be producing this tensor of images in a grayscale in a single channel, and the label will be a tensor of this scalar. This is the index of the class. Okay. So here we have applied the dataset. Now let's build our model. Our model will be different types of models, like it will be convolution in a single part, and the other part will be a linear, because we need to have this classification part. So this classification need to be applied by a linear model, and the convolution need to be applied to reduce the number of parameters and to extract the most important features out of this image. That's just a quick recap of what we have discussed through the previous lecture of CNN. Okay, so let's build the model. Of course, we need to inherit from the module, torch module part, and let's build our two main methods. One is forward, and it takes the image. Okay, and it should return the prediction by the end of the day. Okay, so this is the two main methods of the class or model, and we might have two blocks. I have called it the blocks. So for example, convolutional block and linear block. So the convolution block will be a sequential part, a pipeline of convolutional metrics, like conv2D. I have here input channels, which is pretty much 1, so I can insert it here with a default value of 1 because we are in grayscale. If you are in, if you don't apply the transformation of the grayscale, you can make it 3 and let it work as it is. Also, we have the output channel. So for example, I need to have a 128 output channel. So this will be a matrix, 3-dimensional matrix, which is be height by width by 128 depth. Okay, so each feature, there will be exist 128 feature maps concatenated side by side behind each other. Okay, and after this, the parameter will be the kernel size. I can choose 3, and the stride will be 1. Okay, and then we can use the dot relu and this max pooling 2D, of course. If you have an image of 3-dimensional, you can have this pooling 3D and conv 2D and conv 3D as well. Also, the pooling here I can apply from, for example, 5, or yeah, make it 5, for example. In that case, it will be a large matrix, and it will be taking the maximum item across this kernel, 5 by 5 kernel. And I can make the stride, by default, the stride is as equal to the kernel, but I will make it by 1. So I need to make it walk slowly, and I can copy paste this layer to make another layer of this, and it will be taking 128 as the input, and the output of it, for example, like have like 32 as an output channels. So I compress this 128 feature maps into 32 only. So this is called also the bottleneck. And let's have a 5 kernels here, and this will be 7. Okay. And now we have a point here, like before transforming from this linear block with from to the to linear block, from the convolution to linear, we need first to know what is the output dimension of this. So for example, here I know that the output dimension is 32 by height and by width. So I need here to define what is the width and what is the height, because I need to initialize our linear model. So the linear model should take the input of this number and outputs anything. Like for example, I need to output for example, 256. Okay, and then another linear layer which will be taking 256 and outputting out number of classes. Okay, so you know what I mean. Now we need to know what is the output the output size of the kernel of the feature maps, and this will be flattened, and flattening them will be done in the forward. We will be reshaping this three-dimensional matrix into a single vector, and after this we will be inserting them to a linear layer, and we need to know how many parameters does this flattened vector have. So in order to know this, unfortunately, we need to run it alone. So I need to run the self.block by any random image, and let's call it the feature map, and return this feature map, for example. So let's run this model. Okay, I need to comment this, of course. And this outcast I can also insert through the last part. We have here 10 classes as an output class. Okay, anyway, so let's build our model. It will need the input channels and output channel, which already known. So this model, I can pass through it the transformed images, which is the image batch transformed. And let's see what is the output of this. So, okay, as you can see here, it says like expected 4-dimensional, but got 3-dimension, 10 by 32 by 32. So we need to insert this new axis part because we need to have 10 by 1 by 32 by 32. Okay, so here I can check the shape. So it's 10 by 32 by 32. I need to reshape it into 10, which is the batch size, by 1 by 32 by 32. And now check the shape again. So the new axes have been added. So let's save it in the same object and run it. Okay, the model have produced the output correctly. So let's check the feature map now. Okay, so it's 32 by 16 by 16. You can also, if you don't need to use this and try your own part, it will be also using this, if you remember this equation that we have already run before, like m minus k plus 2p over s plus 1. You can also calculate across this convolution and max pooling, the convolutions and max pooling, and calculate all of it. But I will just run it as you can see here. And we now know what is the number of parameters we need to pass to the linear part. So I will be multiplying this by 16. Okay, so this is the input of the linear, and here, for example, this is the output. I can also decrease this as much as possible. And how to flatten this matrix and to be 10 by something, I can also apply the reshape, as you can see here, with the same time. Like I can reshape the output to be 10 by all of these rest of the axis, concatenate them, multiply them with each other. So it is 81 by 8192. So if we apply also 32 by 16 by 16, it will be the same number. Okay, so that's what we are going to do before passing to the linear block, because here we need to pass to the linear block and pass it to the flattened feature map, but it will be flattened. Okay, so the flattened will be feature map dot reshape of batch size and -1. And now we need to know what is the batch size, so we can take it from the input, as it will be the first dimension. So if I check the size, it will be bringing me all the dimensions. Like I can check it here. If I check the size, it will be giving me all these dimensions like the shape. But here I can check only the first item, like this, B for example, and let all the rest of the items be stored through this underscore that I don't need, and B will have this scalar value. Okay, so batch size here will be holding this number and flattening this feature map and passing it to the linear block. Also in this linear block I can add another for example dropout of 0.2 and another ReLU layer. Okay, in that case you can also apply anything, like you can also apply patch normalization for avoiding overfitting, etc. So this is pretty much how you can work upon, because this dropout will be deactivated through the evaluation function, but only be activated through the training mode. Okay, and this is the linear output, linear fine. And finally we can use explicitly softmax as an output layer, and this will be generating the probabilities, or we can just work with these logits, and after this we use the cross entropy loss function, which implements behind the scenes the softmax. So it will be more stable in the numerical part to let it without any applying any activation function by the end layer, by the final layer. Okay, so now let's start to make this as the logits. So this would be the logits, which is the raw numbers without any activation being applied upon. So let's build our model now again. Okay, can be multiplied 10, 32, and 256 by 10. Okay, so here we have 32. Okay, we need to make it 32 also. That's my mistake. And let's run it again. Okay, so now our model have produced a shape of 10 by 10. It should be 10 images and the output class is 10. So it will be each image will have 10 probabilities. Like this will be what is the maximum number from this, and this will be the output class that the model predicted to be the correct class. Of course, it is random weights for now, but we can, for example, check this by argmax of 1. So it will be producing like all of them is 6. So the model is a little bit untrained or biased to this. Okay, so now let's build the config part, which will be what is the optimizer we need to use. For example, we can use this optim.adam. You can also use any part, but this and pass the parameters, and learning rate can be to a -5. This for example, this parameter have been determined to be working best with Adam. You can also change it as you like, because it's all of this is hyperparameters you can play with. Okay, and we also have the model and the optimizer. We can determine the number of epochs. For this part we can make it just 10 to see what is the progress across the model. And let's start to now work with the engine. If you find anything else, we can also add through this cell. So the engine will have two methods, the train function, and this will take the model and the batches and also the optimizer and the criterion, which is the loss function actually. So we also need here to define the loss function to be a cross entropy. So this cross entropy takes uh, the logits as input. For example, I can pass it here the logits, the output of the model, and then also it takes the true output. Like I can pass it through it the target here, 10 targets, and transform it into tensor, and it will be producing this uh, output here. For example, it will be 2.2, and this will be the gradient we need to apply. Okay, so I'm just telling you how you can work with it. This will be the output of the model. Okay, it will be a matrix, and this will be a vector. The vector here is the label of the true class, and the matrix here will be the prediction probabilities, all the probabilities being applied. Okay, this also will be passed to the training function, and the same function will be in the eval function. We might here start working with the training function. The difference between training and evaluation is that training will be applied back propagation, while evaluation only forward is needed. And so let's get started. So here I have the epoch loss, make it 0, and let's convert our model into the training mode. While in the eval mode here, I need to apply it into the eval mode. Okay, so in this case, we will be deactivating all these dropout and batch normalization if have they been added to the model. Okay, and now let's work on the batch. For batch in batches, we will be first taking the image and the label from this batch. So it will be batch of image, and I'm here extracting this dictionary. If you correctly identified what is this dictionary, it is basically this data set here. So I'm checking the image and the label from this. It will be something like this. Okay, so as you can see here, this is the label and this is the image. And let's then pass it through this forward propagation, pass it through the model. So the model will take this image, and let's have this output, and then we now will be applying backward propagation. Backward propagation is basically 3 steps we need to apply. First of all, we need to zero grad to the to erase all the previous steps we have, and if there exists any random weights, we don't need to make them used by the model in this next step. And then we will be calculating the loss. So first we need to calculate the loss. It will be using this criterion and take the output and the label. Okay, so this loss will be now by accumulating the loss to make it in a backward. Okay, backward here is to accumulate the loss. Okay, it will not be setting the loss, it will be accumulating. Why we are accumulating loss in torch and not setting them? Because we can actually, if we have like a small memory and we don't need to apply back propagation at every step in the epoch, so we need, for example, we apply gradient update every 5 epochs, so we keep accumulating the loss, keep accumulating them until the 5th batch, and then we apply the last part, which is a optim dot step. So this function will be if we need to apply gradient each 5 epochs, so we can accumulate the loss each batch, each simple batch, and after 5 batches we can apply this optimizer. So that's one of the reasons why we accumulate and not add. See? And also we need to apply the optim zero grad within these like these two methods need to be run by together. Okay, so these are pretty much the three methods we need to apply for backward propagation, and then we have this epoch loss. We can add it the loss dot item, and finally we will be returning our loss epoch loss. Okay, so the same exactly same method will be added here, and of course we need the epoch loss again, and for batching batches we don't need the optimizer. Okay, we can have here the model will be passed to this, and we don't need any optimization and or any backward propagation. And also we need to remove any gradient calculation, so with torch.no gradient being calculated through this context. Okay, and this is pretty much the eval and training function. So now let's go to the training loop. First we need to identify here the data loader. So as you can see here, this is the data loader and this is the CFAR. We don't actually run the CFAR now. We have this data set, our defined data set. We pass it the CFAR.train data. Okay, and this is a target. So CFAR.targets, and transformation will be this tr. And this is the train batches. Okay, this is the train dataset, and this is the train batches. And the train dataset will be passed to the data loader, and the batch size, for example, will be 32. Okay, I can make it 10 by now, for example, because maybe I don't have the GPU to run all this data and to shuffle it. Of course, we need to shuffle this. I don't know whether we have this testing dataset or it's a training by default. Okay. Okay. Okay, we have also a test dataset which have this 10K, so we can add them to a new dataset here for the eval function. And instead of CFAR, we pass this for data and CFAR test, and it will be, instead of train, it will be test batches. Okay, and we don't need to shuffle here. The same batch size. Okay, that's fine. So now let's run them, and let's remove this on it. Okay, the training loop, I will be looping for epoch in a range of number of epochs, and I will be passing the train function, passing it the train batches and the model and the optimizer, and finally the criterion. Yes, and this will be training the epoch loss train, and here apply the eval function, which will take the test batches model and don't need the optimizer, and this is the test loss, and we'll be just printing them out. Like here, you can apply train loss Val loss. Okay, and this will be epoch. Let's see if it all run without any errors. Okay, I think it we might be need to reduce this number of patches within our data because the memory is not pretty much fine. But anyway, like if you can work with this in your own side, you can have uh, more idea of how this training function, if you apply it also in a Google Colab or something, you can have a faster, but I'm just flexible with using the Visual Studio. But anyway, here you can change also the CFR dataset, change the architecture of the model and see whether it have better accuracy or less loss. And maybe you can also add a feature within your train function and eval function to calculate also the accuracy, whether it captures the output is the maximum argument, the argmax is the same as the label. So in that case, you can have a good idea of applying more models. Okay, I'll be pushing this notebook to the repo as well. And let's see the next time with the convolution neural network lecture. Thank you and see you next time.